So all the lectures, recorded lectures of previous weeks, you can find it in the YouTube channel that I have shared, and the materials like presentation and notes and codes, everything also you can find over in the comments of the YouTube. Okay, so in the YouTube also, so what I am doing is, I am so I mean these lectures, these TS sessions every week would be 2 hours, right? So some of you might not have, the patience to go through the whole material, like sit through 2 hours continuously and check. Uh, I mean, go through the whole lecture. So what I am doing is that I am, making short videos of some particular specific topics. So out of that 2 hours, I will like make short videos of some particular topics. So recently, like just like today, I uploaded a video on logistic regression, which I actually covered previously in week one. But it is in week one, the whole lecture, if you going to see that, that will be like 2 hours. So what you can do if you are like looking for anything in particular, you can look at the short videos, like it's at 10 to 20 minutes videos maybe, right? So if you're looking, get an idea, you don't have to sit through the whole TS session for of 2 hours, right? So yeah, so that's what I am trying to do. So I think it will be beneficial for you as well if you are looking for any specific topic, right? So yeah, I was saying that today I uploaded a video on logistic regression. So yeah, if you are looking for, so actually, logistic regression is one of the topics that I'm going to cover today. So the today agenda would be logistic regression and support vector machines (SVM). So yeah, but if you want any additional material, so I will refer back to the earlier video as well. So there are some topics which I had covered earlier, and I will refer back to those in today's lecture as well. So yeah, so that is the plan. So yeah, any questions on that? Like, I think, do you find it helpful? Would you let me know? Okay. And okay, so there are two questions. Mainak has asked, what is the difference between feature selection and feature extraction? Right. So you know, okay. So feature selection is when you have. So let's say you are building a model and you have 10 features. Now you have to find out which features are most appropriate for your model, which are the most significant features, right? So maybe you don't have that much computational facility, so that you cannot include all the features in your model. So what you do is select some of the features to decide which features are important, and you keep only those important features, and on those important features you build your model, right? So I think if you go back to the previous lectures, I think you can find it. I don't remember which week, but probably week 3 or week 4. I've covered feature selection in detail. Right? So there are like two topics like forward propagation, backward propagation, in which in the way you which select your features, and then feature extraction. Yes, it's I think it's in week 4 probably. Yeah. So what I will do is that I'll make a separate small video on feature selection and feature extraction so that you don't have to go through the whole week 4 lecture of 2 hours. So I think I'll just cut that part and make a separate video on that as well. But yeah, just to answer your question, feature extraction is, yeah, PCA is a example of feature extraction. So not feature extraction, I would say it is an example of feature reduction. So dimensionality reduction. So basically, in that, what happens is that let's say your model has 10 features, you're not removing some of the features completely, right? So, so you have a, let's say, 10 dimension data. So out of those 10 dimensions, you reduce your dimensions to, let's say, 2 dimensions, and those 2 dimensions will be a linear combination of the initial 10 features that you had. So you're not removing any particular feature completely in feature reduction. What you're doing is just you're putting weights on uh, all the features, and whichever feature has more importance, you're giving higher weight to those, and whichever feature has less importance, you're giving lower weights to those. And by that, you create a new feature, and so that out of 10, you are reducing your feature to 2 features, let's say, and then you build your model on those 2 features. So that is the difference between feature selection and feature reduction, right? Okay. Uh, okay. So Kavita is asking upload video link in NPTEL videos immediately on next day. Uh, yeah. So videos, as I said, like you can go to my YouTube channel actually. So I have pinned the link for my YouTube channel. So here you can go and you can find the videos already. Like this, I am recording as live, so it will be there in my YouTube channel always. You see, right? So yeah, you don't need to wait for whenever you get the link or not. The video will always be there in my channel. So what you do is, again, if you are following my channel, it will be uploaded there only. Like it will be there. It won't be removed, right? So what I suggest is you do subscribe to my channel or something, and then you will get updates on the videos, right? And even like if you gonna check after the streaming, after the live streaming, you can go to my channel and you can find the video. We can move on to today's agenda. Okay, so welcome to week 5 introduction to machine learning. My name is Rohan and I am a TA for this course from ISC Bangalore. And yeah, so today's agenda, as I said, would be logistic regression and support vector machines, right? Okay. So yeah, so in the previous lectures, we have seen linear regression algorithm, right? So why do we need logistic regression? So I think one in previous lectures I've explained the difference between linear and logistic regression, right? So one is used for continuous variables, like linear regression is used for uh, when your dependent variable is continuous in values, whereas logistic regression is used when your dependent variable are discrete in values, right? So, for example, housing prices, example that I gave in the first week, housing prices versus the number of rooms or the size of the room, right? Housing prices, the price of the house is a continuous value. It's not a discrete value. It can take any value between 0 to, I don't know, infinity, right? So, in that case, we will use linear regression. So, whereas logistic regression is used when you have, you know, when your dependent variable can take only discrete values. For example, so let's say you have this data. Okay. So what is the data is? The data is that, so let me explain you with an example first. Okay. So let's say you are doing an experiment on mice. Okay. So you have a set of 100 mice and you measure their weight. Okay. And based on weight, you are trying to detect whether these mice are obese or not. So you're basically trying to see the obesity of mouse based on weight. So what you do is that your x variable is basically weight and your dependent variable is obese or not. So dependent variable could either be 0 or 1. So that is discrete, right? So 0 means not obese and 1 means obese. Okay. So what you do is you plot the weight on the x-axis. So let's say these are different mouse. Okay. And you plot each of the like weight of each of the mouse on the x-axis, right? So this mouse has, let's say, weight of 20 something, I don't know, maybe let's say 200 gram, okay? And this mouse has weight of, let's say uh, 800 gram, right? So yeah. So then these you are, and also you are classifying them as like these mice as obese, and you are classifying this mice as not obese. Okay. So what will happen if you try to fit a linear regression line through this? Okay. So this could be a possible, linear regression fitting that you could obtain, right? But what is the problem with this? Can anybody tell me? So yeah, one problem is uh, this linear regression fitted line could take any values between 0 and 1, and it can also take values beyond 0 and 1. So for example, let's say I want to predict whether a mouse would be obese or not, and whose weight is, let's say, 1 kilogram over here, right? So if you look at this linear regression fitted line, so corresponding to this mouse, the y value would be somewhere, above 1, more than 1, right? So that doesn't mean anything, right? Either your mouse is obese or it's not. So it could take either value 1 or 0. Value greater than 1 doesn't mean anything. Also, it can take any values between 0 and 1, right? So for example, your ma- your you could have some mouse whose weight is something, and you're getting a value of y zero point 0.8. So that doesn't mean anything again. Whether that mouse is obese or not, you don't, right? So that could be a possible problem if you use linear regression for uh, for this problem, right? So what we do is, instead of fitting a straight line, what we do is we try to fit a sigmoid curve. So this is what is called a sigmoid curve, right? And this is what you try to fit. So you see, like if you have a mouse here, the y value that it will get is a very close to 0, right? So this is actually not exactly the y value. This is the probability of the mouse being obese. So if p is very close to 0, so then you will classify that as y equals to 0. So I'll explain in detail like how you compute this curve, and you know uh, we'll see through examples how we can get this curve, and how with some random x value we can get the y value, right? So so this curve has the equation of 1 by, so this thing 1 by 1 plus e to the power of minus b naught plus b1 x. Okay. So depend, and this b naught and b1, these are the parameters that you have to calculate. So so how do we calculate that? So if you remember, we had done gradient descent in linear regression, right? So similarly, we would use gradient descent algorithm to calculate the parameters by optimizing our cost function. So I will get to that. What are the cost function and how you optimize them and how you get the value of p. But for now, let's say you have, got this curve. So you have your data and you got the sigmoid curve corresponding to your data, right? And then let's say if you get a new example, if you get a new mouse, let's say whose weight lies in this part, okay? So then you will see what is the corresponding y value, whether this mouse is obese or not. So you will just see the corresponding y value. The y value would be so this is basically the p value, they said. The p value would be very close to 1, and therefore you classify it as y equals to 1. That is, it is an obese mouse, right? So this is the sigmoid curve, and using the sigmoid curve, you will classify any new examples of mouse that you get as obese or not. Is that clear? Do you have any questions? Okay, if not, let me move on to the next part. Yeah. So Kirti is asking, do we have any loss of information while converting it? Uh, what do you mean by loss of information? And while converting what? Loss of data when converting to S curve. So, so this S curve, that is basically built on all the data in your training set, right? So, for example, you see this graph. So let's say your data set are over here right now, but if your data set has shifted towards the right, then similarly your S curve would shift towards the right. So the S curve will depend on the initial data that you have. So yeah, so whatever the data you take for training, the S curve will be built on that data. It will adjust to that data by minimizing your loss function or cost function, right? So yeah, I think your question will be clear if we uh, study this slide, which is the gradient descent, and what is the cost function that we use for this is so yeah. Again, if you so this is basically the cost function, right? And this is what we have to minimize. And if you are looking for a derivation of this function, I have just explained it in the previous lecture when I was doing the naive Bayes algorithm. So please go through that lecture if you want mathematical derivation of it. Right? But here I'm just explaining what the terms means again. So for example, let's say you have some, yeah, as I said in the previous example, you have some mice and some are classified as obese and some are classified as non-obese. So y is the y value, like whether it is obese or not. So if it's obese, then y will be 1. Not obese, y 0, right? So y times log of h theta x. So h theta x is basically your prediction. So this is this logistic model, this value of the sigmoid function, the value of p basically that is given here. 1 divided by 1 plus e to the power of minus b naught plus b1 x, right? And yeah, similarly, if you have more features like other than weight, if you have like, size or something else, you would have like b naught plus b1 x plus b2 y. B2 y is a bad choice of variable. b1 x1 plus b2 x2 plus b3 x3 and so on. Like whatever the number of features that you have. Right? So yeah, so h theta x is basically that p value, right? And minus 1 minus y log of 1 minus h theta x, right? So, yeah, any questions on this? So this is so in case of linear regression, if you remember, we use the least square cost function, right? And then we applied the gradient descent on that least square cost function. Here we are applying this cost function, which I derived in the previous video, and we are trying to minimize this cost function and then find the values of this. So here I have written b naught b1. So these are basically theta parameters, theta naught or theta 1, whatever you say. This is just naming. So we want to find those theta naught theta 1 or b naught b1, and then we want to find, then we'll find this p value, And accordingly, as I said, we can classify them as, obese or not obese, right? So is the concept clear? Is the whole process that we are doing, is that clear from a conceptual point of view? We'll go into the mathematics, but is the concept clear before that? Okay. Okay. So yeah, you can ask me questions like if you are, stuck at any part or you need more clarification. So how do we minimize this cost function? Again, we use the gradient descent method. Uh, yeah. So basically, what you do is whenever you want to minimize some function, what you do is you take derivative of that function. So the derivative and you equate the derivative to zero. So that will give you a minimum of that function, right? So and then, but in the in this algorithm, gradient descent algorithm, which again I have explained in one of the earlier lectures, is what you do is you update this theta parameters, whatever theta parameters that you have. For example, b naught or b1. In this case, you have only two parameters, b naught and b1, or you can say theta naught and theta one, right? So you update those parameters. You start with some initial value of theta naught and theta one, and you update them by using this function, right? So theta naught minus alpha del j del theta, right? And you iterate this till you converge to a minimum, right? So here are questions like, you know, how would you know whether you have converged to a minimum? And another question is, what is this alpha? Alpha is called the learning rate, right? So yeah, again, these two questions I have answered in one of my previous videos, but I will just quickly, explain them again. So, how do you know whether you have converged to a minimum, whether your theta has come to a minimum? So, you can understand that by seeing that, okay, so, after some iterations, your theta would not change by very much. Your theta would remain, let's say, I mean, would change by very small amount, and then you know that okay, my theta is not changing much, so I have converged to a minimum. So that is the way to know whether you have converged to a minimum or not. And secondly, what is alpha? So alpha is the learning parameter, so this will determine how fast you are converging to a minimum. So for very high learning rate or learning parameter, what we will do is that you will take bigger steps towards the minimum of the function. Whereas for small alpha, you will take smaller and smaller steps towards the minimum. So smaller alpha would, increase computational time, whereas bigger alpha would reduce computational time, but at the same time, it will, uh, it might have some chances of uh, not converging. It might diverge as well, right? So again, please go through the previous lectures uh, to know about these answers in more detail. Okay. So yeah, so basically you repeat this and you find the optimal value of theta naught and theta 1, and you find the value of p, and from there you can classify whether this is 0, y is equals to 0 or y equals to 1. Now, uh, okay, so let me, so I will do the calculation in a minute, but if you like take the derivative of j with respect to theta, you get this term. But like how did this term comes in, right? So I'll just do the calculation of how del j del theta is this value, right? So again, let me come back to my notepad. Yeah, in the meantime, if you have any questions, please ask me. So it is gradient descent algorithm. So the algorithm is theta j is theta j minus alpha times del j del of theta j. right? So what is your cost function? The cost function is minus yi log of h theta xi h theta xi minus 1 minus yi log of 1 minus h theta xi, right? This is your cost function. And what is your h theta? H theta xi is 1 divided by 1 plus e to the power of minus theta transpose x, right? So that is the sigmoid function that we saw, right? This is called the sigmoid function, which has that S kind of shape, right? Right? And it has values between 0 and 1. Okay? So this is 8 theta respect to x. Okay? All right. So what is del j del theta? This term that we have to calculate. This is the term that we are calculating. Del j del theta. So what is del j del theta? So we are taking derivative of this expression. Okay. So it is minus yi. So derivative of log is 1 by x. So h theta xi times derivative of h theta with respect to theta. So this is just chain rule, right? So I think everybody understands this, or do you need any clarification? Let me know. So I'm just applying chain rule here. Okay. So minus 1 minus yi. Again, derivative of log is 1 by x and del of h theta del theta. Right. Right. Okay. So one thing here, there will be one minus. So del of minus h theta. So if you see, we're taking derivative of minus h theta, right? So here is the minus sign that we have, okay, in the expression, right? So because of this minus sign, we're taking derivative of this. Because of this minus sign, another minus will come, and this will be minus h. So this minus minus will become, actually it will become plus. Okay, so this will be plus, right? Okay. Now, one thing that we have to calculate is del of h theta with respect to theta, derivative of h theta with respect to theta. So basically, then we'll consider this line. We'll take derivative of this h theta. So again, 1 by x is minus 1 by x square. That is e to the minus theta transpose x whole square times derivative of e to the power x is e to the power x times derivative of theta is x transpose. Okay. And here again, there is one minus sign, which will cancel with the minus that we got from here. So again, so I'll just write this explicitly, but this minus minus would become plus. So one minus coming from derivative of this, another minus coming from derivative of 1 by this thing, right? So I'll just do it plus, yeah. So this is the expression, right? Now, this can be written as h theta square. Okay, let me, so what is this term? This term is basically h theta square, right? If you see h theta is this thing, this is just square of that times e to the power of minus theta transpose x times x transpose, right? We can like write it like this. Okay. Now, in other words, you can also write e to the power of minus theta transpose x as okay. Wait, we will do it. We'll do that later. Let me let me rewrite the del j del theta term. Okay. So from here, we see del j del theta would be minus of yi times this 1 by h theta that was there earlier times del h del theta. So del h del theta we got as h theta square xi times e to the power minus theta transpose x times x transpose. Okay. So I'm just substituting del h del theta over here. Plus 1 minus yi. Okay, Valli has raised a hand. Yeah, please. Is there a question? Okay, if not, let me proceed. So 1 minus yi times 1 by 1 minus h theta. Wait a minute. Yeah, 1 minus h theta xi times again del h del theta. So that is h theta xi square, h theta square, e to the power minus theta transpose x times x transpose. Okay. Now we will see what is 1 minus h theta. 1 minus h theta is 1 divided by 1 plus e to the power minus theta transpose x. That will give you e to the power of minus theta transpose x divided by 1 plus e to the power of minus theta transpose x. So that is basically e to the power of minus theta transpose x times h theta, right? Okay. So far, so good. All right. Now we'll just substitute uh, 1 minus h theta in this part, this region. Okay. We'll substitute this value and this over here. So again, from here we get del j del theta equals to minus yi. So if you see 1 h theta and 1 h theta cancels, so basically h theta xi times e to the power minus theta transpose x times x transpose. okay, plus 1 minus yi, 1 divided by, yeah, we are replacing 1 minus 1 minus h theta with this thing, h theta xi times h theta square xi e to the power of minus theta transpose x times x transpose. Okay, we're just replacing that. So if you see e to the power of minus theta transpose x cancels with e to the power of minus theta transpose x, 1 h theta cancels over here like this, and you will have minus yi h theta xi e to the power of minus theta transpose x x transpose plus 1 minus yi. What is remaining is h theta xi x transpose. Now, there is another manipulation that we have to do. Okay, so I'll write it over here. So if you see that h theta equals to 1 divided by 1 plus e to the power of minus theta transpose x, right? So basically you multiply it. So 1 equals to h theta plus h theta times e to the power of minus theta transpose x. So from here you will get e to the minus theta transpose x equals to 1 minus h theta divided by h theta. Okay. So I think the ink is little bit lower. Let me, okay, let me write it properly. So h theta equals to 1 divided by 1 plus e to the power of minus theta transpose x, right? So simplifying this, I will get h theta plus this thing, okay? And from here, you can get e to the power theta transpose x equals to 1 minus h theta divided by h theta, okay? And now we'll just substitute e to the power minus theta transpose x value over here. So this is h theta times 1 minus h theta divided by h theta x transpose plus 1 minus yi h theta x transpose. Okay. So again, this h theta cancels, and you are left with minus yi 1 minus h theta x transpose plus 1 minus yi h theta x transpose. Right. So this will give you minus yi x transpose minus h theta yi x transpose plus h theta x transpose minus yi h theta x transpose, right? So h theta yi x transpose, h theta yi x transpose cancels, and you are left with, uh, yeah, basically h theta minus yi times x transpose, right? So, yeah, I can see that, this calculation is a bit, you know, mathematical, but I think you should do it at least once by yourself, right? So this is actually the h theta minus yi x transpose that we saw in our uh, PPT over here. So yeah, so this is h theta minus yi times x transpose. So that is del j del theta, and this is how you update your theta at every step until you converge and find the optimum value of theta naught and theta 1. So I agree that was a bit mathematical, but if you have any questions, please ask. We'll see the application part now. So I think the application part will be a little bit more interesting. And but if you have any questions on the calculation part, please let me know. Right. So how about we do one example uh, on this, on how to calculate this value, right? So let me go to my notebook. So yeah, Everybody can see my notebook, right? Okay. Let me zoom it. I think yeah, it's visible, right? So yeah, so this is the example that we have. Let's say we have four uh, mice, and each of them has this kind of weight. So first mouse has weight 5, second has weight 10, third has weight 15, fourth has weight 20. And the first two mice, we are categorizing them as not obese because they have kind of lower weight, whereas the remaining two mice, we're categorizing them as obese. So if you see, obesity value is 0 for the first two, and obesity value is 1 for the last two because they have higher weight. Right? So what we do is we build a logistic regression model. So this is the function that you're using from sklearn linear model, and this is the logistic regression fitting that we're doing over here in the model part. We're building the model over here. So here, what you can do is you can, after you have built the model, you want to check uh, what are the coefficients like theta naught and theta 1. So this is how you do it. Okay. Okay. So you see, you are printing the model intercept, which is basically your theta naught, and your model coefficient, that is theta 1 or b naught, b1, whichever way you see it, right? So this is the value of your theta naught. This is the value of your theta 1, right? And based on this, what you do is calculate the sigmoid curve and you calculate the p value, uh, and then you classify them as obese or not obese. So let's say uh, let's say you have a new example, right? So let me do an example first. Okay. Okay. So as I was saying that, these are the weights. So weight is 5, 10, 15, and 20. And your obesity in this case is a 0, 0, 1, 1, right? So from there, you are getting your theta naught by building the logistic regression model. You're getting your theta naught as, let me see, theta naught is minus 9.24 and theta 1 is 0. Let's say 74. We are rounding up to two decimal places. Right? So theta naught is minus 9.24, theta 1 is 0.74. Right. So now, so if I just plot a graph of this function, how will it look? So on this case, you have weight on the x-axis. On this y-axis, you have obesity. So this is one example which has weight 5. Another example which has weight 10. So these are marked as 0, not obese, and these are marked as obese. So you have another two examples which have weight 15 and weight 20. 15, 20. Okay. So these are marked as obese, right? So let's say you have another example which has value, let's say 25. Okay. Now you want to calculate whether this example would be marked as obese or not obese, like whether this will have 0 value or 1 value. So, the sigmoid curve, if you are following so far, your sigmoid curve will be something of like this. Okay. So you can see that, 25 would be classified as, so like this, it will be classified as obese. So you already have an idea that it should be classified as obese. So you want to see whether it is really getting classified as OBs or not, right? So what you do is for another value 25, you want to find the value of p. So p is 1 divided by 1 plus e to the power of minus uh, theta naught plus theta 1 x. Okay. So again 1 divided by 1 plus e to the power of minus theta naught is your minus 9.24 plus theta 1 is 0.74 into 25. So that is the value you get, right? Any questions? So I think someone is asking, is this course too tough? Yeah, I don't think it's too tough. So you can, I mean, you can skip the mathematics part if you want, but what is important is you follow the conceptual part or the machine learning part that you see. Right. So I'm just doing the calculations for your understanding, but in assignments you might have to solve some problems. So for those you need to do this calculations, right? But your conceptual part is more important, right? So yeah, uh, let me calculate this using a calculator. In the meantime, if you have any questions, please let me know. Okay, so yeah, you can do this calculation, and this value would come out to be very close to one, like up to 4 decimal places. It is like 1.0000, so on, right. So you see, uh, now you see, like, right, that this will be classified as OBs as we predicted earlier, right? Okay. Similarly, you can take other examples. You can say what will be the value for, if your weight is, let's say, 13, right? So it will come very close to this part. Maybe it will come, the p value would be somewhere, let's say p equals to zero point 0.7, right? Or something like that. So then maybe, this is just an example that I think maybe the exact value would be something different. But the point here is that how will you classify if you get a p value of 0.7? Will you classify it as obese or not obese? That's the question. Does anybody know? Obese. Okay. Kavita is saying obese. Yeah, but why? I mean, uh, see, you can choose the cutoff as zero point 0.5, right? So let's say if you choose the cutoff as zero point 0.5, so whatever the p value you are getting above than 0.5, you're classifying them as obese, right? So yeah, I think Kavita is saying greater than the threshold, right? So, but how do you decide the threshold? That's the question. Like whether the threshold should always be zero point 0.5 or the threshold could also be, let's say, zero point 0.8, right? Or zero point 0.2. Okay. So threshold, how you determine the threshold, that depends totally on you and depends on the problem statement, right? For example, you don't want to miss on any obese mouse. Okay. So you want to keep your algorithm very conservative. You don't want to aggressively, uh, aggressively classify them, right? So you want to say that, okay, I want all the obese confidently, right? So I don't. So what will I do? Is in that case I set my threshold to be lower. Like I will set that p equals to zero point 0.2, so that I capture all the obese samples confidently. So basically, in that case, what will happen is that I would capture all the obese samples, but in return, there is a trade-off. And the trade-off is that I will also capture some false positives. So basically, I'll capture some samples which are not obese, but still I will predict them as obese. So I will have some false positives as well. On the other hand, if I set my threshold too high, then what will happen? I'll capture some false negatives, right? Is that yeah? Kernel is saying false negative. Is that concept clear? Right? Okay. So Ravi is saying question number 2, assignment 5, unit explanation. Uh, okay. So yeah. So I cannot solve the questions of the assignment, but I can explain you the question. So basically, it's saying that you have a data set with n equals to 10 features and 100 examples. So you have 100 samples and 10 features. After training a logistic regression classifier with gradient descent, you find that it has high training error. Yeah, so you have high training error and does not achieve the desired performance on training and validation sets. Which of the following might be promising steps to take? So one is use SVM with a nonlinear kernel function, reduce the number of training examples, create or add new polynomial features, right? So if you have high training error and also high testing error, so think in terms of bias and variance. So again, I have explained it in one of the previous videos. Think in terms of bias and variance, in which case you have high training error and high testing error or cross validation error. And how do you reduce those training and testing error, right? So how to reduce bias, how to reduce variance, and so on. So think in terms of those. Okay. And I think then you will get your answer. Right? Okay. All right. Okay. So I think we have covered how to calculate the threshold part. Okay. Now, yeah. Now you have built your logistic regression model. You have got your result, and yeah. So this is again to recapitulate your true positive, false positive, and confusion matrix. So this is called the confusion matrix. So this is the true class. That means these are actually positive, these are actually negative, and this is a predicted class. These are predicted to be positive, predicted to be negative. So if your true class is positive and your predicted is positive, then they are true positive. If your true class is negative, predicted class false positives, true class is positive, predicted to be negative, false negatives, true class negative, predicted to be negative as is true negative, right? Okay, Kavita is saying how to set threshold. Please explain. Yeah, I will explain through this why this confusion matrix again. Okay, so if you see that if you are keeping your threshold to be very low, right? So yeah, let's see in this example. So if you are keeping your threshold to be very low, what will happen is that you are capturing more and more obese people, obese mouse, and along with that, you will also capture some mouse which are not obese, right? So, so they are predicted to be obese. So predicted class is 1, but actual class is 0, right? So from the confusion matrix, you see predicted class positive, but actual negative. So that means they are false positive. So you'll capture some false positives as well, right? And what will happen if you capture false positives? So if you see from this formula, right? This is the formula for accuracy, for precision, and for recall. So if you capture more and more false positives, your precision will go down. Your precision will decrease. Whereas, because you see in precision formula, false positive is in the denominator. So higher number of false positives, higher is the denominator, the total value would decrease, precision will decrease. On the other hand, recall. recall will increase, right? What if you do the opposite? Okay, let's say if you set your threshold to be very high. So in that case, your false positives will decrease because you are very aggressive in determining who is obese, right? So you are pretty much confident that all the obese that you have captured are truly obese. So your false positives will decrease. But what will happen? The in the population which are not obese, which you are predicting as not obese, some obese mouse might go into the not obese population. So what will happen there? Then your false negatives will decrease because you're predicting it to be zero, predicting it to be negative, but they are actually obese and they are actually positive. So your false negatives will increase. So in that case, the recall would decrease, but your precision will increase. Okay? Because false negatives increase, recall will decrease, and precision on the other hand will increase. Is that clear? I know that's a lot, but take some time to think about it and see whether it makes sense to you or not. So it depends on you know whether what is your problem statement. If you want to capture all the OBs, you want to be sure that you capture all the OBs, then you want to set your threshold high. Or if you want to capture all the non-obese mouse, then you want to set your threshold. Uh, yeah, I think I said the opposite, but yeah. So yeah, I'll repeat that again. If you want to capture all the uh, obese mouse, so what you will do, you will set your threshold low. On the other hand, if you want to capture all the non-obese mouse, you will set your threshold high. So it depends on your problem statement, right? So yeah, again, this is the formula for accuracy, precision, recall. We had discussed this in earlier lectures, and this is the F1 score. So you see that there is a precision recall trade-off that we just saw, that if you want to increase precision, you might have to decrease recall and vice versa. So F1 score measures the balance between both precision and recall. So yeah, it sets uh, it's a score which makes sure that both of your precision and recall are you know on an average level, so that neither one goes very low. And the way you measure your uh, model performance, uh, it could be based on these four parameters: accuracy, precision, recall, F1 score. So, right? So, okay. So, there is something called, AOC RUC curve. Okay. And this is a curve between true positive rate and false positive rate. So, I will not go into this right now. Maybe in one of the uh, So what I'll do is that if I get time at the end, I will explain what is this, or else I would try to make a short video on this topic, and I will upload it later on YouTube. Right. So keep following this. But this is one of the important things that people use to determine which is a better model and which value of threshold to be used. So this is actually another measure, like which should be your optimal threshold, right? That this is a way to uh, calculate the value of the optimal threshold. So again, I will try to upload a video afterwards uh, on this particular topic, or if I get time at the end, I will explain this. In the meantime, we'll see another hands-on uh, exercise on logistic regression. So let me go back to my notebook. I hope it's visible. Okay. All right. So again, we are just so this is a data set that I have used earlier when I was explaining the KNN model. Right? So this is a diabetes data set, and which I am loading, and here is how it looks. Okay. 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 Let me just clear the output once again, and let me run it again. Wait a minute. Okay. So this is how the data looks like. Okay. So these are your X variables, and this is the Y variable. So the Y variable says that whether you have diabetes or not. Y outcome equals to 1 means you have diabetes, outcome equals to 0 means you don't have diabetes. And these are the X variables, the data that you have with you, based on which you will determine whether that person has diabetes or not. So for example, someone's glucose level is 148, blood pressure is 72, skin thickness this, and so on. And this will be the uh, values, okay? Whether you have diabetes or not. So these are some of the pre-processing steps that we had done earlier. I will just not go into the details. You just look at the statistics of the X values, and here you calculate, you just do the missing imputation. Again, I have explained this in previous lecture when I was explaining the Kernel algorithm. So you see how many people has diabetes. This is the one. So one is 268. 268 people has diabetes and 500 people don't have diabetes in the data set. You want to make sure that you have significant amount of population in both the segments, like 0 and 1, so that you are not, your model is not biased towards any one population. So these are some of the pre-processing steps that you do. Again, this is a correlation matrix. I've explained in detail in the previous video. So there's a color plot of a correlation matrix. This captures it beautifully. It's in a colorful way. So that just means that blood pressure is basically related to, let's say, glucose. What is the correlation between blood pressure and glucose? That's 0.22, right? So if you increase glucose by 1 unit, your blood pressure will increase by 0.22 unit. So this is what correlation means. This is what how you need the correlation matrix, right? Now, model building. So here you just set your X variables, which are all the columns except the outcome columns. You just drop the outcome column from the data set, and your Y variable is the outcome column, right? Now you split your data set into training and testing data. Your testing data is 25% of the total data, right? You split it, and here you build the logistic regression. You import this function, and you build the train the model, basically fit the model. Okay, and yeah, and you predict it in the test set. But whichever x values you have, you predict them, and you store those values in y pred. Now, now what you do is you calculate what is the confusion matrix, right? So again, this is a uh, okay. So this is again a colorful way to see the confusion matrix. So yeah, as we saw that uh, this is the predicted 0, this is the predicted 1, this is actual 1 and actual 0. So basically, this green part 41, this is the number of true positives that you have. 116 is the number of true negatives that you have. Okay. This one, 26, these are predicted to be 0, but actually they are 1, right? So they are uh, false negatives. They're falsely tagged as 0, falsely tagged as negative. These 9 are false positives. So they are falsely tagged as uh, positives, right? This is the confusion matrix that you have. And again, from with this, you can calculate precision, recall, F1 score, and so on, right? So this is the name of the function, classification report. So if you just use this function, it will give you the precision, recall, F1 score, and so on. Based on that, you can determine the uh, the performance of your model, right? So that is it for logistic regression. If you have any questions so far, please ask. Do we have to follow the, so Prerna is asking, do we have to follow the commands too for the exam? So by commands, you mean the Python uh, commands, Python code? But no, no, no. So for exam, you don't have to remember the Python codes. Uh, I think there'll be numericals and some explanation type questions based on theory only. But basic commands, I think you should remember always, like what how to calculate. For example, let's build the model, which is the function that you use, that is a logistic regression function. So these functions are names are also very intuitive. From which module do you have to import this scalar or linear model? You know how to calculate confusion matrix. So from this function, from this module, matrix module, you import the confusion matrix function and so on. So these you can I mean, it's better if you remember, but you don't have to memorize the names, right? So yeah, any other question? So if not, we'll just take a 2-minute break and then we will come back and start with support vector machines. Okay. All right. Okay. So if you guys want more examples on logistic regression, you can, as I said, I just uploaded a video on logistic regression, which I covered in first week one. So you can just look at that example. That is another example based on spam classifier email. So you receive a lot of spams on your email, and it is a way to classify how to classify those emails as spam or not. And based on that, how to calculate true positive and false negative, how to calculate precision, recall. So I've done those. I've done a numerical on that on as well. So if you want more practice on that, you can, uh, look at that as well, right? Okay. So if you don't have any questions on logistic regression, we can move on to support vector machines. Okay. Okay. Uh, so I think so. In the way, if you have seen the lectures by the professor, you can see that there are a lot of mathematics involved in support vector machines. But I will try to explain in a way such that there are no at least minimum mathematics are required, right? So I'll try to explain it in a conceptual and from a machine learning standpoint, right? And how to uh, actually implement it from an implementation point of view, right? So okay, so let's say we have seen an example of logistic regression, like how you can classify a set of mice into obese or not, right? Now, let's say you have the same example. You have some set of mice, and these are the weights of those mice, and you are classifying them as obese or not. So the red ones are the not obese, green ones are obese. So these are your data. Okay, this is the data. Let's consider the first row. Okay, I'll then sequentially go into the next uh, next rows. Okay, so in the first row, this is your data that you are given, and you have to classify them as mice or not. So sorry, classify them as obese or not. So you can like visually see that if you like draw a line over here or here or here, you can just separate them into uh, obese or not obese. So anything that lies on the left of that line is not obese, right of that line is obese. Okay? But the question is how to decide which line to take. Now come to the second picture. So here, let's say if you have chosen this line, okay. So is it a good way to classify obese or not obese? No, right? Because let's say if you get a new example, which is given in shown in black over here. So this example would be classified as obese according to the line you have drawn, because on the right of the line, you are just telling everything is obese. So this example lies on the right of that line. But you see, this example is closer to the set of non-obese mice, right? And it's farther away from the obese mice. So what will happen is that this is not a good idea. This is not a good line to classify them as obese or not. Right? On the other hand, let's come to the third picture now. What if you choose this line as your classification line? So everything on the left is not obese, like obese. So this is a, a better choice actually, because this is uh, not as close to this to the red set of points, and not as close to the green set of points as well. It's somewhere in between. Now, what will happen? Okay, so there is one terminology before moving on. So whatever the line is, the distance of the closest red point is from this line is this distance, okay, and from the closest green point from this line is this distance. So these are called margins, okay. This is just a terminology, right? So for example, if you shift this line towards your left, the red margin decreases, whereas the green margin increases, right? So this is one way to classify this. But again, the question remains like, which is the best orange line that could classify these examples? So now moving on to this thing. Okay. So if you uh, put this orange line exactly in between the nearest green example and the nearest red example, that is basically called the maximal margin classifier, because then only you will have this maximal margin. So if you shift this orange line towards the left, this red margin will decrease. So that is not the maximal margin. Okay, but only if you put the orange line in between, uh, like exactly half the distance in between the red and the green points, then you will get the maximal margin. And this classifier is called the maximal margin classifier. This is also known as support vector classifier. Okay, it's clear, simple, like there is no math involved, right? Only you are just, you know, visually uh, judging the point where you need to classify this into OBs and not OBs, right? Okay, so what if, now come to the next picture. What if your data has some outlier? Okay, for example, let's say there is one mouse which is not obese but has a higher mass, right? So you have this. In this case, what will happen is that your maximal margin classifier would fail, because where will be the maximum margin classifier in this case? In this case, it will be between this green point and this red point. So somewhere in between, right? But let's say then if you get a new point over here, it will be classified as not obese, but it is actually obese, right? Because it's closer to the obese set of points. So then you run into a problem. Then the support vector classifier or the maximal margin classifier would run into problems when you have outliers, right? So what you do is then you come up with a method which is called a soft margin. So what is a soft margin? So it is basically you allow misclassifications in your data. Okay. So let's say your data is outlier and you allow, let's say I allow one misclassification at least. So I by allowing one misclassification, what will happen is that you are just ignoring this misclassification. So you are allowing them and you just ignore this red point, because although this is misclassified uh, as uh, as per the new orange line, this line, okay, as per the new orange line, this will be classified as obese, but this is actually not obese. So you will allow this misclassification and you ignore this point completely while building your model, and you will build your model uh, on the remaining data. So again, this will be a new margin, right? And you determine the maximal margin again based on your based by allowing one misclassification. And then this new margin is called the soft margin, and this new classifier is called the soft margin classifier, right? Is that clear up to now? Okay. Okay. So now the question is, how many misclassifications should you allow? In this case, we are allowing one misclassification. Should we allow one? Should we allow two? Should we allow three? And so on. How many misclassifications should we allow? Right? So the answer is simple. It just depends on your data and the number of misclassifications that you can allow you have to test it on your cross validation. So this is a hyperparameter. You can think of it as a hyperparameter that you can tune, and you can just tune it on your cross validation data. For example, what will be the error if you allow one misclassification in your cross validation? What will be the error in cross validation if you allow two misclassifications? And so on. You test it and you cross validate your data, and finally, whichever number of misclassification gives you the least error, that will be the number of misclassification that you can allow. So that is the best performance model, right? Okay, that is your best soft margin classifier. Okay. Now, let's uh, go into a little more complicated example. So let's say in case of, I mean, instead of, just a weight, you have two features based on which you have to uh, determine your support vector classifier. So in this case, you have weight, another could be, size. So you have two parameters, two features, x1 and x2. And your data, these are the green ones, let's say, which are not obese. These are the blue ones, which are obese. Okay. Now, in this case, what will be your support vector classifier? So unlike in the one-dimensional data, your support vector classifier is just a point below which is not obese, above which is obese, right? On the other hand, in this case, your support vector classifier would be a line, okay? So which will allow the maximum margin. Again, in this case, if you see the margin is this distance, this is the margin, right? Similarly, if you have a three-dimensional data, your support vector classifier would be a plane, a 2D plane, and and so on. For a four-dimensional data, it would be a 3D hyperplane, right? And so on, right? I think it's clear, right? Okay. Now, what are support vector machines? So till now, we saw what is support vector classifiers, right? Now, let's explain this with the help of another example. So let's say let's look at a different example, right? Let's say this is the dosage of medicine, okay? And uh, let's say you're taking some medicine, and the red points are the cases in which the medicine is not working. So this is a zero, let's say y equals to zero, means medicine is not working. The green points are the points where medicine is working. So if you take this much dosage of medicine, your medicine works. So if you take very low dosage of medicine, your medicine doesn't work. On the other hand, if you also take these examples, which are very high dosage of medicines, your medicine doesn't work. Whereas if you take an optimal dosage, your medicine actually works, right? So you can see, right, that this example is a little bit more complicated than the previous one. In the previous one, you had simple, you can separate this with a point. But how can you separate these examples with a point, right? You cannot have, if you draw your line over here, let's say in the second example, second picture, if you see, let's say if you draw your orange line over here, and you classify all the points to the left as not working, and on the right you are saying that the medicine is working, but that doesn't work, right, in this case, because you very high dosage of medicine also doesn't work, right? So what will you do now, right? This support vector classifier algorithm that we saw is not uh, valid in this case, right? So simple idea, what you do is you project your data set into a higher dimension. You so this is a one-dimensional data, right? You just have the dosage parameter. Now what you do, you project this one-dimensional data into a higher dimension. And how will you do that? That's the thing that we'll see in the remaining time. Okay. So uh, you have learned about PCA and LDA, principal component analysis, linear experiment analysis in week 3, I guess. And you see how you reduce the dimension of the data. Like somebody has asked the question about feature reduction. So you know how to reduce a higher dimension data to a lower dimension using PCA and LDA, right? If you don't know how, then you can go back to and we look at lectures of week 3, I suppose. Okay. And but in this case, what you are doing is exactly the opposite. We are increasing the dimension of data. We are taking a one dimension data and increasing it to higher dimensions, two dimension, three dimension, or so on, right? So what we'll do is let's take this data and map it to a 2D data. Okay. So how to do it? So let's just, if you look at this picture now, let's just take all the points and square it. Okay. So in this case, you take the dosage of this point. So this is, let's say some dosage, let's say 2. The dosage and mg is 2. You square it, 2 square is 4, and you plot it in this xy plane. Okay, this is a 2D plane. So on the x-axis, this point has coordinates 2 comma 4, right? So on the x-axis, this is still this value. On the y-axis is the squared value of this dosage. So what will happen is you similarly map, all these remaining points, and this is the result that you get, right? Is the mapping clear? How it's being mapped, right? Let me, explain it with in my notepad again, if you are not here. Okay. So let's see. Okay. So your initial data is just dosage. So let's say this has dosage 1, this has dosage 2, whereas I'm representing the, okay, okay, let me use a different color for, so the red ones are the ones which are working actually. So this is, let's say, this value is 5, this value is 6, this value is again 10, 12. So if you take very high doses like 10 and 12, your medicine will not work. If you take medium dosage like 5 and 6, it will work. For dosage like 1 and 2, it will not work. So you just map them into a two-dimensional space. So again, your y-axis will still be dosage, and your x-axis will be dosage, y-axis will be dosage square. So the first point, this point, will be mapped to a point 1, 1. So this is one from x-axis and one from y-axis, right? So this is the first point. This is being mapped to 1, 1. The second point will map to 2, comma 4. Third point will be mapped to 5, comma 25, right? Let me write this in red. Okay. So this point is 5, comma 25. This point is, let me, yeah, these are not according to the scale. So this will be 6, comma 36, another point. And then again, the last 2 points would be, you know, over here, 10, comma 10, comma 100 and 12, comma 144, right? So you have successfully projected them into a two-dimensional space. right? Now you see, now what you can do is you can draw a line like this, right? And thus you can separate your positive examples from the negative example, which you couldn't have done in your lower dimensional space, right? So this is the maximal margin classifier or support vector classifier, right? And your margins in this case would be the distance from this point, and the other margin would be, let's say, distance from this point. This will be your margins, right? Is the concept clear? So you're doing nothing, just projecting your one-dimensional data into a higher dimension, right? Okay. So you see, like there is you don't have to do any mathematics, or there are no high level mathematics involved over here, right? So we just learned, what is a polynomial kernel. So this is the idea of a polynomial kernel. So you see, people, talk about kernels, they use so much mathematics, and they calculate so much stuff, and but ideally you do not require anything. This is so simple. You just project your one-dimensional data to a high-dimensional data. You square it. You just square the values and plot them in a high-dimensional data, see which is the line that is fitting in the best, right? I think, yeah, as I said, I will not do any complicated mathematics. uh, that was done in the lectures. So this is a way to learn it simply. So anybody can understand. That's the point. Okay. So we just learned what is the idea of a polynomial kernel. So here are some of the kernel functions that you can use. For example, like you might have thought, like, why did I just square it? Why not cube it? Right? Why not take to the power of 4 or to the power of 5 and so on? Right? So you can do so much stuff. Why just take polynomial? We can do other functions. We can like transform them with some, let's say, exponential or sine function, or we can take any function, right? Why just square it? So I think those are valid questions. You can do it actually. So for example, you see that for the polynomial kernel, so this is the kernel. So x1, x2 plus c whole to the power t, right? So what you are doing here, in our case, what we just did is our d is basically 2, right? And c was 0, right? So basically this will just become x1 times x2, right? So I'll again come back to this, like how do I relate this kernel function to for example, to what we just did, right? So let me come back to the whiteboard again. So we saw the kernel function for polynomial is you know x1 times x2 plus c whole to the power t, right? So again, these are one point that I want to make before moving forward. So which value of C to choose, which value of D to choose, these are dependent on your data. You could choose, again, these are hyperparameters, and you need to fix the value of C and D based on cross validation. So you can train your model based on different values of C and D, and finally, check which is which value of D is giving you the least cross validation error, and that is the uh, model that you should take. Okay. So just to explain what is the physical meaning of this kernel, right? So Kij would be, let's say, Xi Xj. So in this case, we have only one feature, that is just let me see once. All right. Okay. Okay. So anyway, so in this case, our xi are the dosage value, right? So what is this physically doing? What is xi and xi times xj plus c whole to the d physically doing, right? So it is just creating. Uh, so okay, let me come back a little. So what is KI? What is this kernel? Physically, what does it mean? So let's say you take this example as your ith example, the first one. This example as your ith example. And let's say this example as your uh, jth example. So based on this, you'll get some value, right? So if you see it's getting 1 times 6 plus c whole to a t, right? You'll get some value. Now, the question is, what does this value mean physically? Physically, it means that how closely related are these two features? How closely, sorry, the examples. How closely related are this one example and the six dosage, right? For very close examples, for example, 1 and 2, right? These are closely related, they are close to each other. You will have a lower kernel value, lower value of k. Whereas for 1 and 6, you will have a higher value of k. Is that clear? Okay. Okay. So that is what the kernel basically physically means. Okay. Okay. Someone has asked, Menak is asking to explain the last figure. So which figure? You mean the dosage, the two-dimensional transformation, or the kernel part? Both. Okay. Okay. So initially, what we had is this 1D data. You had dosage. Your black points are the points which are uh, in which the medicines are not working. So black means y equals to 0, and the red points are the one y equals to 1. Okay. Now, using this data, you have no way to classify clearly. So earlier, what we used to do, we used to draw a line and say that okay, whatever is the left of the line, y equals to 0. Whatever is on the right, y equals to 1. But now here you have two additional points, 10 and 12, right? Which also have y equals to 0. So you cannot do this line thing, right? So what you do is you project your data into a higher dimension, two dimension. So one way to do is, just take the square. So for example, this is 1. You take the square, 1 square is 1. You plot the point in two dimensions. Similarly, you plot all other points. This is a 2 comma 4. Okay. You take the second point, square it, plot it, right? Similarly, you plot the other points. Now in the two dimension, what you can do is you can draw this line, right? This line that you have drawn. And you can say that, okay, whatever is in the right of this line, it's classified as y equals to 1. Whatever is on the left of this line is classified as y equals to 0. That is the way you do it, right? So you're projecting it into a higher dimension data. But physically, you actually do not project it. What you do is you calculate this kernel function. This kernel function in the background is actually projecting it, but physically, you don't project your data. So the kernel function will just give you a value of uh, which is a measure of how uh, closely related are two points, right? So yeah, but to understand it, to understand how the kernel function performs, it's easy to visualize it in uh, as a as a projection into a higher dimension, right? Is the explanation clear now? Is the explanation clear? Now, let me explain through an example, like how this kernel function does this. Okay. So let's say, uh, you have this, let's say two values, okay, and two values of dosage. One is A, one is B, right? Now, uh, what will be the kernel value of this two? Let's, move this. Okay. So let's say you take A times B plus, let's say you fix your this thing C value to be, let's say 3, okay, for now. And you take the D value to be 2, okay, for this particular example. Now, what will the kernel value for these two examples? So if you just square it, it's simple, this square plus 6AB plus 9, okay. Now, you can write this as a dot product, okay, right? Let me see. This, okay. There should be some factor of root 6 over here. Yeah. So what is a dot product? So let's say if you have 2 points, x1, y1, and another point is x2, y2. So the dot product between these two vectors, so if this can be represented as two vectors, right? So the dot product between these two vectors would be x1, x2 plus y1, y2, right? This is what a dot product is. This is the dot product between two vectors. Similarly, if you like, this is your two vectors, right? This is one vector and this is another one, right? So dot product will be multiplying the corresponding values. So root 6a times root 6b, that will give you this term, and a square times b square will give you this term. 3 times 3 will give you this term, 9. Okay. So you can write this kernel. This kernel is just a value, right? Based on the value of A and B. Let's say A is 1 and B is 2. You can calculate the value of the kernel. This will just give you a number. This will just give you a number. But this number, the way to think about it is you can think about it like a dot product between two vectors, right? So as I said, what are the two vectors? The two vectors are root 6a, a square. Let's ignore this for now because both this is same in both the cases. 3 is same. So it can be represented as root 6 times a comma a square. So how do you use this kernel when you are uh, transforming your data into higher dimension? So what you will do, your x-axis would be root 6 times a. So earlier a was here. So let's say initially A was here, B was here. So next time when you are using this kernel, what you will do? You multiply A times root 6. You plot this into new position. This is your root 6A. Similarly, multiply root 6B. This is your new root 6B. And then you will also do A square. So let's say this is the A square. This distance is A square. Right? So this is your new representation of A. Similarly, new representation of B would be root 6B comma B square. This is your new coordinate. Okay. New coordinates are root 6A square, root 6B B square. Right. This will be your new representation of your data in higher dimension. Right. Is that clear? So Prerna is asking x10 and x12 value would be larger, although they are close. Yeah. So you see, you can like calculate the value of x10 and x12, right? Wherever they lie using this formula. So, but not formula, but using this method, depending on whatever C you choose and whatever D you choose. In this case, if you are choosing 3 and 2 as C and D, So you can map. So if your x is 10, so it will map to root 6 into 10, comma 10 square. So wherever the point is in the xy plane, 10 root 6 and 100, that's where your new projection of a in higher dimension would be. That's clear, right? But instead of actually projecting the data into higher dimension, you're just calculating the kernel. You're just calculating a value, calculating a number, which explains the relation between 2 points, in this case A and B, in higher dimension, right? Without even going into higher dimension, the kernel tells you what is the relation between the 2 points in higher dimension. That is such a powerful method. That's why this kernel method is so powerful. Okay. Now coming back to the slides. Okay. So I just explained what is a polynomial kernel, and linear kernel is just using as it is. It is just basically not using any kernel, equivalent to not using any kernel. So you're just not projecting it into a higher dimension. You're just keeping the dimension same. And Gaussian kernel, this is another way to uh, also called radial basis kernel, another way to transform your data into higher dimension and check the relation between the two points in higher dimension. So you could, as I said, you could have any function. You not necessarily need to have a polynomial function. It could be a exponential function as well. And this is a sigmoid kernel, which is a tan h function, right? Hyperbolic tan function. You could have any kernel of your choice, right? But not necessarily all the kernels will give you better performance, right? So you have to see which kernel is giving you better performance and what are the parameters that you choose. Like in this case, you have to choose gamma parameter, which gamma is giving you better performance and so on. Like you have to see that, okay? But these are some of the examples of the commonly used kernels, right? We'll see a hands-on exercise on the usage of all these kernels, right, after this slide. So that will become more clear on how to uh, how to tune the hyperparameters like CED, gamma, and so on, right? So again, this is an example of let's say 2D data, right, on this thing, and the red points are, let's say, y equals to 0, green points are y equals to 1. So you can see a clear boundary could be a kind of a circular kind of a boundary, right? But in some cases, it might not be that obvious. In this case, it's obvious. So what you do is you use the Gaussian kernel and you project it into a higher dimension data. So now you see, okay, this set of points are clearly forming a different cluster. So in this case, it is just mixed together, right? You cannot have a straight line which is separating uh, separating the red with the green points. You cannot draw a line. But in this, when you're mapping it to a 3D data using any other dimension data using a kernel, you can see, okay, you can draw a hypersurface, hyperplane, like this decision surface that they have shown, to clearly separate the red points and the green points. So this is how a projection actually looks like into a higher dimension, right? And then the hyperplane will become basically this circle. And then you can draw a circle in the 2D as well to see which is the best support vector classifier, right? Okay, so Priyank is asking why we ignored 3. Uh, where did we ignore 3 in the example? Mhm. Oh, acha, you mean this 3. Okay. Okay. So why we ignore 3 is that you might not ignore, I mean, you can take 3 as well, but you see, this will add another dimension to the data. So it will be a 3D data in which your z-axis value is 3. But since in both the cases, like both the vectors have same z value, so that means in the 3 dimension, they both lie in the same plane, right? So so that's why you ignore 3. Yeah. But the question is like, yeah, like Priyanka is saying that if it was different, like in this case, if it was 3 and 2, then we cannot ignore. But since it is same in both the cases, we can ignore it, right? Because as you see in the this will add a third dimension, and the third dimension value is same for both the vectors. So it is basically lying in the plane in the third dimension. That means it's just an 2D surface, right? Is that fine? You can just take 3 as well, but that will just, complicate the thing. Okay. Mainak is asking which one to use when. Suppose I have a tabular dataset which I have normalized. How to select which kernel I should take? Yeah. So Mainak, I will answer your question when we will do the hands-on. Again, there is no, you know, particular kernel that I can see. I can say that okay, this kernel will perform the best. But yeah, let me show you an example on hands-on, and then you can better see it, right? So let me come back to my notebook. Everybody can see my notebook, right? Okay. So here is a data set that I am using, and okay, so this is a universal bank data set. So I will upload the data set in the Google Drive. Okay, so you can like try it out and test other stuff that you after this session. Okay, so let me just explain the data set once. So these are different people, data of different people. For example, people with ID 1 has age 25, experience of 1 year, income 49,000, and so on. Like you have so much data of different people, and your Y variable is the credit card variable. So what does it mean? That 0 means you don't have a credit card, 1 means you have a credit card. Okay. Now, if a new person comes whose age, experience, and income you have to predict whether that person has a credit card or not. Right? Simple. It's as simple. Okay. Now, you just read the data, you do some pre-processing. For example, you could drop the ID and the zip code because, yeah, ID is just a randomly assigned serial number, right? It doesn't help in determining whether that person has credit card or not. Similarly, zip code doesn't determine whether we have credit card or not. Or zip code is actually, categorical variable. It's not a numeric variable. Based on the zip code value, you cannot say, okay, this person has credit card or not, right? And so on. Like, okay, after dropping this, you just see the data again. So these are some of the pre-processing steps that we do, and we have done in previous week's lectures as well. So again, this is the correlation matrix that we just saw earlier as well. So this just shows the correlation between the different variables in the data. Okay, and difference between all the features. And this is the dependent variable, the y variable. So you can see what is the correlation of each of these features with the credit card. So for example, let's say which has the highest correlation, right? So this 0.28 I think is the highest one. So CD account. Okay. So if you have a CD account, I don't know what that means, but whatever. If someone has this have a high value of CD account, then he's predicted to have a higher value of credit card. Right? On the other hand, very low correlation would be let's see 0028 0024. Okay. So I guess this one income. Income is least correlated with credit card, right? Uh, and the negative correlation means more the income, lesser is the credit card value, right? Which is I don't know. It seems counterintuitive, but anyway, whatever the data is, right? Okay. So that's it. And now what you do is you just see how many uh, credit card equals to 0 values you have, how many zeros y equals to 0 you have, that is 3530, and how many ones you have. So just to check that you have sufficient number of ones and zeros in your data set. And again, this step just normalizes the data. Okay. As I said, why is normalization necessary? It's because you basically have uh, the different variables, the different features have different values, ranges. For example, age could take a range between 18 to, let's say, 60. Experience income could take a range between 20,000 to 1 lakh maybe, right? And so on. So different variables have different ranges. So to normalize them is to take them within the same range, right? Okay. So yeah, now you just define your x variable, y variable, and you know this step just split the data into training and test set. Okay, and now in this step you just build your support vector classifier. Okay, and you store the predicted values in y pred variable. Okay, right, and you just print the model accuracy. Okay, so accuracy score is 0.749, right? So here, till here, you are not using any kernel. Okay, you're not using any kernel, and that gives an accuracy of 0.749. Okay. Now you just print the confusion matrix. So this is your confusion matrix. You see, you have a lot of these are uh, predicted as negatives, right? So these are basically false negatives. These are actually positive, but predicted as negative. So you have a lot of false positives, right? In this case. And similarly, you can check precision, recall, and so on. Right? Okay. So now, coming back to the question, like which kernel is best? Now, what we'll do is we'll use several different kernels. First, let's start with the linear kernel. Okay. So, using a linear kernel, if you see, again, you just check the accuracy. It's again 74.7% accurate, and still you have a lot of uh, false negatives, right? And you can get the precision recall and so on. Now let's see what will be the accuracy if I use a Gaussian kernel. So if you see using a Gaussian kernel gives you a little bit of higher accuracy, 74.9 compared to the linear kernel, it was giving 74.7, right? But still you have a lot of false negatives, right? And these are the precision and recall for Gaussian kernel. Next, we try polynomial kernel. Okay, here we are trying with C value of 1, right? Here we are getting a 74.9. So similarly, like if you again, I was saying, if you can go to uh, you know Google and see what are the parameters that this function text takes. Uh, Let me see. Yeah. So this is the function SVC. Okay. So you can just Google and see SVC Python. Okay. So this will just give you a clear documentation of whatever the uh, parameters this function takes. So for example, C equals to 1, you see, and degree of the polynomial that you want to use. So this will give you a degree 3 polynomial, right? Kernel, RBF, the Gaussian kernel if you want to use or so on, right? So here for polynomial kernel, C equals to 1, and I think the default degree they are using is 3. Okay, so this will give you a third degree polynomial, right? So with that, you are getting an accuracy of 74.9. Let's try with let's say just for fun, degree equals to 5. Okay, and let's see what is the accuracy. So okay, so the accuracy goes down 73.1. Let's try with degree 2. Okay, now accuracy is 74.9. Okay, let's try with degree 4. So you can do these things, right? You can play with this. The codes will be available and you can play with this. Okay, now what will be the confusion matrix? Similarly, you can see the confusion matrix, the precision recall values for this polynomial. Okay, right? And finally, we can try out the sigmoid kernel, right? The tan H function, right? And similarly, C equals to 1, and calculate the confusion matrix. In this case, your accuracy goes down 62.9. Okay. But you see, you are getting a lower number of false negatives, right? So depending on, yeah, your precision, uh, yeah, basically your recall actually goes up. Your precision goes down. So, okay. So depending on whatever parameters that you want to, whatever performance metrics that you want to see, and you can try out all these different kernels, right? Okay, and you can also change the parameters of all this kernel. For example, here if you are trying c equals to 1, you can try c equals to 3, c equals to 5, and so on. Let's say, in this case, you can try out degree 3 polynomial with c equals to, let's say, 3, uh, and, you just calculate the accuracy and precision, recall, and all those things you can calculate, right? So, yeah. So I think that answers your question, which kernel to choose, right? You can just look at which kernel gives you the best accuracy or best precision, best recall, and then uh, you know choose the best kernel for your data, right? So yeah, so that was it. Yeah, so like always, we'll end the session with some questions, and here are some of the questions that you can see. So what are the other alternatives of sigmoid function? So you saw how we use the sigmoid function in logistic regression to find the uh, probability, and from there we can classify it as y is 0 or y equals to 1. So you can use other functions apart from sigmoid, the S-shaped curve. So you look into all those different functions, and you can use those functions to train the logistic regression model that we saw in our hands-on exercise. Okay. And second question is how to choose the optimal value of threshold in logistic regression. So we discussed that a bit, but you also read about how to use the ROC AUC curve to determine the best model and how to choose the best value of threshold based on the ROC AUC curve. Also try to plot the ROC AUC curve for the example that we did in Python. And last question is show how a radial kernel is basically a polynomial kernel in infinite dimensions. So radial kernel is nothing but a polynomial kernel in infinite dimensions. So it's the D parameter that you that we are looking at for the polynomial kernel. For if you go to infinite dimensions, that basically reduces to a radial kernel. So you can just search about it and look for it. Yeah, I think I suggest you to you know play with the codes that I will post, and then you will get a more better idea of how these work. Yeah. So yeah, is there any question? Please ask. Yeah, where to find the notebook? Uh, so I will post a Google Drive link of where you can find all the notes, the uh, the yeah, where you can find the notes and PPTs and everything, the notebook as well. So the link will be posted in my YouTube comment. You can find it over there. So it will be a Google Drive link. There you can find all the materials starting from week 1. Okay. So if you see in the YouTube video of my previous weeks, you can find the notebooks in the comments or in the description of the corresponding YouTube link. Okay. Any other questions? One versus all, can you explain regarding SPM? Uh, what do you mean by one versus all? Question in assignment. Which question? Question number? Can you tell me the question number, please? Okay, I think question number 6. Okay, yeah. So suppose you are dealing with a 3-class classification model and want to train a SVM model on the data, and that for that you are using the one versus all method. How many times do you need to train the SVM model in this case? Okay. Okay, so yeah. Now, so all the examples that we saw have two classes. Uh, Basically, either y equals to 0 or y equals to 1. Right? Let's say you have 3 classes or 4 classes or more classes. So let's say you have y equals to 0, y equals to 1, y equals to 2. Let's say you have 3 classes. Now, how will you perform this algorithm? How will you perform SVM? So one way to do is, let's take you, let's at the first, you take y equals to 0 and you take other examples which are not 0. So y equals to 0 and y equals to not 0, right? So in that way, you build your model and you draw the SVM classifier that you get. So that is for one class. So for one case. Okay, first case. Next case, what you do is you draw another classifier by taking y equals to 1, and that is at one class, and whichever classes that are y not equals to 1. So that is your another classifier that you get, another model that you have to build, right? And on the in the third case, you take y equals to 3, and then again you take y not equals to 3, right? So that is the thing. I mean, repeatedly you have to do, okay, for all the classes. If you have more than 2 class, is that clear? So you take one class at a time and you know uh, perform the SVM repeatedly for all the subsequent classes. Okay. Any other questions? Okay, if there are no other questions, then thank you for joining. Uh, yeah, so good luck for the assignments, and you know, mm, I think we'll see you again. We'll meet again next week. Okay, thank you. Thanks. Okay, Kavita is asking, is the kernel used for similarity? Yes, similarity in higher dimension, not in the low dimension, right? Because in the lower dimension, if you see uh, this point and this point are far apart, right? These two red points are far apart in the lower dimension. So this will have a higher kernel value. But in the higher dimension, this point and this point would be closer, and you know that's how kernel measures the similarity in the higher dimension. Okay. Okay. Thank you. See you next week.